to all of you. We are again here on the sir. Dr. I.A. Palani is an associate professor and the Dean Research and Development in the IIT Indore. He has completed his PhD from the IIT Madras in the field of laser assisted semiconductor processing. Sir, during his PhD, he received the Kasyu University Fellowship from the Japan to pursue his research from the period of 1 year. Later, after his PhD, he got an offer from the Kasyu University to work as a research scientist from 2010 to 2012. Sir has joined IIT Indore in the year 2012. He was the founding head for the discipline of metallurgical engineering and the material science. Sir, area of research include mechatronic system design, shape memory alloys, laser assisted micro manufacturing, surface processing. He has published more than 100 international journal publications in the reputed journals, 150 conference publications, 8 book chapters. He has filed 6 patents in the field of shape memory alloys. He also nominated as the president of the SPIE student chapter for the year 2017. Sir is a recipient of the Research and Innovation Alumni Award for the year 2015. Sir has guided 10 PhD and 15 MTech student till dates. Sir has been implementing projects from the DRDO, ISRO, DST, SERB, DAD, Russian Science Foundation, JSPS, and Royal Academy of Engineering, UK, of worth rupees 8 crore. He has a strong collaboration with the industries such as Volvo, Acer, John Deere, Webco, etc. Sir was invited the visiting professor in the St. Petersburg University, Russia, IF Dresden, Germany, Casio University, Japan, Cambridge University, UK, and Cranfield University, UK. Sir, we are feeling very grateful to have you right now with us. On the behalf of Technical Event Cell, Parallel University, I welcome you, sir. Now, over to sir.
Okay. Thank you very much for giving me this opportunity and inviting me to present this lecture on the biomimicking. So a special thank to Dr. Om Prakash Shukla for inviting me for this lecture. So without taking much of your time, so we will go to the presentation. Hope you could able to see my screen. Okay. So the topic which we are going to discuss today is something called as biomimicking robot. So as far as this biomimicking robot is concerned, it's quite an interesting field where when we try to talk about robot is concerned, the major concern for adapting it for biomimicking is this actuator. So in this lecture, so we will be discussing about some of the actuators, some of the smart actuators, and how these smart actuators are used for biomimicking. So before going into the presentation, so I would like to just give you a brief intro about our institute. So our institute is almost like a 11 years old institute, IIT Indore. So I'm almost from its inception. So it has a 330-acre campus. In fact, this is a very good bird view, which shows the overall massiveness of the campus. And part of the campus is a thick forest where we could see some kind of leopards coming into it. And this is something about my group. So I have a strong group with PhD and postdoc students, and we also have a master team and master students who are working with us. And this is the lab portfolios where we work on automation and control, laser and optomechatronics, and smart material base. In particular, on smart material base. In fact, we are one of the pioneer in developing smart material, especially shape memory alloys from our laboratory. Now, as far as this, when we talk about this biomimicking robots, so as far as in this biomimicking robot is concerned, any robot if you take, so we will be having a sensor, an actuator, and a control system, which is going to be a key element in the robotic systems. So like based on your applications, we will be selecting our sensors and actuators in such a way that we optimize it for an appropriate application. For example, if I want to create an arrangement, something like this, where I have a limb movement over here, and if I want to mimic this limb movement, so the conventional actuator, what we know is a motor. So just to give be more precise, so an actuator is a system. Basically, it converts any form of energy into a displacement. Whatever displacement it might be, either it might be a linear displacement or it might be a rotary displacement. but when your output is a displacement, then we call it as an actuator. Suppose if I want to mimic this arm, so for this, I need to employ certain amount of motors in this. So if you try to closely observe, so I need to put a motor over here, over here, over here, and then based on my degrees of freedom, I need to employ more amount of motors in it. Okay, so in some cases we will be using a pneumatic based systems, etc. As an alternative approach. So if we can think of a material which can work in such a way that this material has a capability for a biomimicking application, then it is easy for us to select that material as an actuator and use it for our application. Okay, so before going into this application, there's a fundamental question which comes in your mind. When do I call it as biomimicking? Why should I need to go for biomimicking? So as far as nature is concerned, so nature used to give lots of input to us. Like in fact, I would see a best mechanical system or a best system. If I would like, if we need to identify a best system, the best system is our human body. So because it has a capability to convert some form of food to an efficient work to be done. In fact, if you try to look into your ball and socket arrangement in your body and your digestive system in your body, etc., these are completely an integrated system, which has a very good which acts as a very good example for a control, for a sensing, as well as for an actuator. Like, especially like let me just give you an example. Like people used to say, so go for early morning walk to reduce your fat. Okay, this itself is a very good theme. So where your actuation characteristics is being tickled, and then you are trying to burn your fat. Okay, so if I try to look into this, especially with this biomimicking capability, etc. So two things I'm mainly fascinated with. So one is our butterfly. So basically, if I try to closely observe the overall characteristics of a butterfly, one thing most of us know about its variation in color, so which shows its influence of its optical property. So if I try to probe into this optical property of the butterfly, so the optical property is basically been well the pattern which is available on this butterfly. In fact, this pattern is deciding my optical property of the butterfly. So based on that, you are trying to get a different color of the spectrum. So which means that like for any kind of material, if I want to give its shade to it, I don't need to give a paint coating to it, but instead of that, if I try to change my surface texture, then automatically by just changing with respect to the wavelength of light, I can just create the color what is required. So that is what basically it tries to teach us. So now by changing the surface property, you are trying to tune your property of the material. Second one is a feather in of these birds. See, this color from the feathers, in fact, that is quite interesting. So it is of lightweight, and it has a capability to lift the 3 to 4 times, in fact 10 to 15 times of the weight of it. So like if I am thinking to develop a robot, so basically an aerofoil based robot or an aerodynamic robot, so basically if I try to mimic my feather kind of arrangement, then I am just incorporating some kind of capability to my robot to lift on its own and to make it to move forward. So this is what we learn from this feather kind of structure. Next, if I try to talk about two different interesting facts. One is your aerodynamic, or I would say your fluidic based structure. Second is holding the system, basically a wall climbing or a suction based mechanism. See, you might have seen these creatures climbing on the wall. So the interesting fact in this is, like in the case of lizards, etc., there is a suction mechanism which is available over here, and that suction helps it to walk or to move against the acceleration due to gravity, against the gravity. Okay. So in fact, the interesting part in this is if I try to closely observe in the feature of these kind of lizards, so you could see a cup kind of arrangement, and this cup has a small protrusion in this, which creates a suction in this particular region, so that this will be highly helpful for me to hold its weight. Okay. Second, you take a dolphin. So nowadays, the tire are being inspired by the dolphin. In fact, whenever a car is released from some of the companies like Mahindra, so they used to depict the natural animal, so that we all know. Basically, it is trying to depict its aerodynamic behavior and its influence of its aerodynamic to behavior towards the efficiency. So that is what we are trying to work upon. So now here in this case, if you see, so we have kind of surface. So based on the surface, or based on the characteristics of the surface, which these kind of lizards or these kind of animal works. So we can just mimic those surfaces, and we can just employ it in our robot for getting the actual condition. So that is what we are trying to see in this lecture. So before going into this lecture, so we come back to the smart materials. Like my entire lecture will be completely focusing towards a smart material and how these smart materials are utilized for an robotic application. So in fact, this is the family of the smart materials which are available for my purview. So if I need to select these smart materials for my application, so I need to consider two different parameters. One is my actuation stress, and one is my actuation strain. Basically, the actuation stress and the actuation strain will take care of my energy density. So we are trying to categorize these different family of smart materials in this window, and based on that, by keeping this as a criteria, we can select our smart materials for our applications. Okay. So as far as the smart materials is concerned, you have a electrostatic ceramics, we have a piezoelectric structures, we have a magnetostructive ceramics, and then we have the shape memory alloys. So piezo means we all know about it. So as far as the piezoelectric structure is concerned, so it's a kind of a crystal where when I try to apply a load to it, you get EMF coming out of it, and vice versa. When you try to give an EMF, you get a displacement coming out of it. Okay. So in the case of shape memory alloy, so this shape memory alloy is of our own interest because the reason is it has a very good energy density. And most important thing is this shape memory alloy are metallic based, and it is highly responsive to heat. So let me just show you a small video. So in this video, so this we have taken it from a reference where we could see there is a kind of lotus flower kind of arrangement which will be available. So I will just play this video for you. Okay, so hope you could able to see my screen, and this is the video. Okay. So in this video, if you have a lotus flower kind of arrangement, which is completely integrated with the shape memory alloy petal kind of system. So this petal kind of system, so what it is doing is when I try to heat it, it blossoms. And when I try to cut off the heat, it comes back to its shape. So the interesting part of these systems is, so through this we have a heat which is passing through it. So we have a heat which is passing through it, and this heat makes the petal to deform, and when you try to cut off the heat, it comes back. Okay, so this is one of the main characteristics of shape memory alloy, which almost helped us to look into the shape memory alloy behavior of it. So as far as this material is quite interesting, which is responsive to heat, and it gives a very good energy density and a displacement. So that is what we have seen with this material. But in order to study the mechanism, basically we would like to go into the history and see how it is being used. So as far as this shape memory alloy is concerned, so it was developed in the year 1938. So we call it as, commercially, if you see, it is called as nickel titanium naval ordnance. So that is why in a commercially we call it as nitinol. So these nitinols are available in the market. So if I try to fundamentally look into the mechanism of it, so it is something like how your phase transformation occurs in the material in the same way it happens. Like if you have a solid ice and when you try to heat it, you get a liquid, and further heating the liquid, you get a gas phase. In a similar fashion, as far as in this material is concerned, so you initially the material is in a austenite phase. I'm just cooling it, make it in a twinned martensite. So when I try to load it, it gets a deformed martensite. When I try to heat it, it comes back to the austenite phase. So here I'm just keeping my temperature and my load into the purview. Okay, so this will give you a better clarity where we could see, like I have a small string, or I have a small strip with me. So this strip, I am just bending it. So when I try to bend it, what happens is, so this is on a martensite phase. This is the deformed martensite. And when I try to heat it, it comes to an austenite phase, and then it again comes back to the martensite phase. In fact, this is an electrical actuation. So where when I try to heat it, it is trying to pull it in this direction. So this is a cycle where I am just giving a load and the temperature. So when the temperature cuts off, it pulls the spring, and then again it comes back. Even in the hot water actuation is concerned, so here we are just expanded the spring. When we try to put it in a water, it comes back to its shape. So the major key in this is, so I have a heat which is supplied to my SMA material, and then in turn I get a displacement. So when you try to consider your displacement, or when I try to use it for my actuator, my response time and the load bearing capacity, basically the energy density, is going to play a major role. So this is being well taken care by this shape memory alloy, which makes it a useful material for for our robotic applications. Okay. So as far as the family of shape memory alloy is concerned, so these are some of the material which exhibit shape memory alloy behavior, like NITA, NITA CU, CU is written AL, CU ALNI, and FE based SMA structures. These shape memory alloy structures are fed into a fixture kind of arrangement. So in these fixtures, so whatever shape you require or whatever actuation you require, accordingly you can just put it up and you can work it out. Like for example, I have an arrangement over here. So in this arrangement, what I'm doing is, so I'm just fixing up my fixture. So in this fixture, I am just putting up my structure, and I am just switching it between the austenite phase and the martensite phase. So when I am just trying to switch it up between the austenite phase and the martensite phase, so it gives me flexibility to switch between the shapes, whatever I require. So based on my requirement, so I have made my fixture, and I am just trying to train my structure based on my requirement. Okay. So now let us take some examples where shape memory alloy based structures has been used for such kind of biomimicking capability. In fact, this is one good example where what we have done is, so we have a kind of a SMA integrated composite structure which is used for jellyfish kind of arrangement. So this mechanism is called as an inchworm mechanism. So this inchworm mechanism is almost similar to your what do you call it, this earthworm mechanism. So how you see your earthworm, so similar to this inchworm also moves, and it gives you a flexibility to move forward. Okay. Second thing is, this is a meshworm kind of arrangement. So in this meshworm, we can just integrate our shape memory alloy structures, and you can see a deflection coming out of it. In fact, I can just show you a video which shows how the system works. So this is an octopus kind of arrangement, which is being integrated with a shape memory alloy based structure. So in this octopus, you could see, so based on your actuation, so you can see the movement. So whichever area you would like to actuate, so based on that, you can move back and forth, and you can give an appropriate motion to it. Right, like if I want to move it in a forward stroke, I have a 2 pushing arm. Okay, so here the major concern in this is actually we have a capability to take care of the buoyancy. Okay. In fact, this video will give you a better clarity about the electrical actuation of the shape memory alloy structure, where I have a spring and I have a load. Initially, it is on a austenite phase. Now I am heating it. It is moving to a martensite phase. Now, because of the load, it is coming back to a twinned martensite. Once it completely gets stretched, and when it reaches its limit, then an austenite phase will come into the picture. So in a similar term, if we can put it up, so this is hot water disk where we are just trying to immerse our shape memory layer structures. So the shape memory layer structures are in the twinned martensite phase, and we are trying to immerse it inside the liquid, and it gets compressed. And this is in a phase where we are trying to insert it inside a water, and we see that it is taking up its shape. Right. So hope this will give you a clarity about how shape memory alloy has its own application towards biomimicry. Now, let us discuss some of the case studies which we have demonstrated in our lab for a biomimicking capability of these shape memory alloy structures. So one capability is something like we want to demonstrate an earthworm as well as a motion of an earthworm as well as a motion of a caterpillar. Okay, like let me just put the application directly to you. Like I have a tree, so I want to make a robotic system having a capability of earthworm so that it has a peristaltic motion, something like this. And another one is it should have an arrangement of a motion of a caterpillar where it has a two anchor crawling like this. So what happens is on an alternatively actuating it, it can climb the tree and then it can be either used for surveillance or some other applications. So we want to develop this for an agriculture unit because like a person, a coconut tree is there and he want to inspect how the coconuts are. So these kind of systems can be developed, agro-based systems, so that it can climb the tree and it can evaluate. So this is sorry, one arrangement. So we made it in our lab. So for that, we took two different crawling. So one is an earthworm-based peristaltic crawling. So another one is an caterpillar-based two anchor crawling. Now, our major so we have identified our application. So now our major focus is what kind of actuator we would like to choose and what kind of configuration of the actuator should we need to look into it. So for that, what we made is, so we took shape memory alloy based spring, and we had an idea of integrating these spring towards a kind of a polyamide kind of structure so that we can have a biomimicking capability. So that is what an idea we had in mind. So for that, what we did is, so we had a spring and we just applied an SMA. We did some theoretical analysis to it to start to investigate or to see its capability towards our application. So in fact, we went for a different boundary conditions and we applied our electrical biasing to it. In fact, this is a complete modeling and theoretical investigation we did to study the heating and the cooling behavior of such kind of SMA springs. So this is a thermal image camera. So using a thermal image camera, we were trying to investigate the capability of these shape memory alloy springs towards exerting the force as well as towards the peristaltic and the crawling motion. Okay. So now we require a body of that particular system. So for that, what we took is we took a PET raw material, something like this. This PET raw material was inserted in a solid mantle, and we went for a furnace, and we almost switched so that it has a capability of some kind of flexibility towards the system. Over which, what we made is we integrated our shape memory alloy spring, so that when we try to actuate the shape memory alloy spring, initially it is on the austenite phase, and then you get a kind of a actuation coming out of it. And these are some of our characteristics, like pet and as well as an annealed pet, which was kept into it. And this was our configuration. So in this configuration, so we want to do a bending analysis. So what we made is, so we went for a different configuration. So one configuration is you have a braided tube. So these braided tubes are integrated with shape memorialized structures on the top, and on in another configuration, what we made is the shape memorialized structures were well deposited was well crawled on the soft foam. Okay. Third interesting actuation what we made is, inside this tube we made an arrangement something like this, where we had a 3D printed structure. These 3D printed structures were embedded inside the unit, and by alternatively actuating it, you can give a motion to the system. Okay. So this is a kind of motion what we got, and this is a kind of a braided structure which we did for a design configuration. So for our application, since we want to use it for some kind of agriculture-based application, so we want to go for a open loop system. So this is the overall configuration of our open loop system. So this is the soft firm kind of arrangement what we made. So in this we had a programmable power supply. So we integrated our programmable power supply, and LDS sensor was used. So this LDS sensor will be highly helpful for me to monitor the behavior of it. And so basically, since this was on an internal arrangement, so we went for a laser displacement sensor to train our robot for our applications. Okay. So one important question you may ask is, how reliable is your actuator, your shape memory alloy actuator? So for that, we did some kind of reliability test. So what we made is, since if I try to understand my actuator, so in this actuator, not only it is going to displace, it is also going to carry the load of. So what we did is, we made a small test setup kind of arrangement. In this test setup, this is a shape memory alloy spring, and this is the load which is being available over here, and this is an LDS arrangement which is being connected to a DAC and a computer. So by alternatively actuating it, so you can see the overall reliability and life cycle behavior of it. So what we made is, we almost discretize our system into two. One is the heating cycle, and the other one is the cooling cycle. And this was our load arrangement. So in this load arrangement, we changed our load to 1.5 Newton, 3.5 Newton, and 2.5 Newton. And we were more interested to see when it was getting failed. In fact, the interesting part, or the interesting observation what we could observe with this system is that even when we were running more than 1 lakh cycle, so there was no any variations or any disturbance were observed. So that was an interesting part which we could observe with this. And this is our exact performance evaluation we did on the structure. So this is the kind of mesh worm kind of arrangement. This is how we have integrated the spring, and we are trying to program it for some kind of angle orientation as well as theta orientation. So this is the bending angle with respect to time, and this is with respect to the recovery. So what we did is, we try to vary the actuation behavior, and we were trying to look into the bending characteristics of it. So when you try to actuate it, so you will be able to know how much is the bending required, whether that bending will map your requirement for climbing a tree or something like that. And in order to investigate the overall behavior, or I would say especially the bending behavior of it, so we went for a flux sensor. So in this flux sensor, what we made is, so this flux sensor is quite interesting material. So it has a capability to easily get integrated with the system. Second most important thing is, whenever there is a bending is there, you can easily measure the flux sensor signal coming out of it. So in fact, these are some of the performance analysis which we made with the flux sensor. So where we could investigate the bending angle and with respect to time t. And then we could also understand the influence of the bending angle towards the different peristatic as well as the crawling motion. Okay, so to give you an easy understanding, so this is the way the upward bending was taken into consideration, and this is where the left side bending, and this is how we went for a configuration for a right side bending. So that, and alternatively actuating these springs will be highly helpful for me to move along the case. So in fact, this video will show you a better clarity how we have performed the bending. So you could see the response time of it. So in this response time, this is your actuator and this is your braided structure, and this is a kind of bending arrangement we made, and we had some attempts towards chair climbing, as well as we also had some attempts towards two anchor locomotions, etc. Okay. Now, one interesting thing, one a major problem which we observed with this is, on a lab scale, it is easy to use a kind of power supply. But when we try to use it, when we want to use it for some kind of reserved environment, like for example, so you want to use it in some kind of a nuclear power plant, or you want to use it inside a chamber, it is completely encapsulated. For example, I have a gas cylinder. So inside the gas cylinders, I want to do some kind of switching operations where I want to integrate these kind of maximum robot. So we did some interesting study. Like till date, robots are actuated only with the power supply. But first time we have actuated using a laser, because the actuator which I have is a response to heat. Okay, so for me it doesn't require any kind of power source. If I am giving a source as a heat, it can work on it. Okay, so what we did is, so we had a laser in our laboratory, basically a small 50-watt laser. So we used that laser to see how it is actuating the spring. In fact, this is the spring, and this is the load which was being employed to it. So the spring was actuated with the laser, and we were trying to see its behavior in detail. So, but the major problem with actuation with the laser is, as far as laser is concerned, we all know a huge amount of energy is interacting with the material, but it will end up in certain amount of what you call a kind of removal of the material. So we should be careful when we are trying to use the laser for such kind of applications, so that what happens is your energy is less, and then you can have an actuation behavior coming out of it. So for that, we did a huge amount of experimental trials, like with respect to number of passes, then with respect to displacement, and we also went for a pass and a power calculation to see its overall behavior. And this is the laser which we used, and we were trying to look into its capability towards power and the time. Okay, see, this is the kind of arrangement. So you could see a laser which could easily pass through it, and it was directly actuating my system. Okay, so the interesting part in this is, your each and every finite bending can be easily controlled using the laser pulse. So this was an interesting area which we would like to work upon. So overall, with respect to this particular module, so the observation what we could see is, so it has a very good thermomechanical analysis. Basically, in fact, on an Indian context, we are the first to show such kind of mesh-worm based soft robotic structure with a higher bending angle, and now we are in the verge of transferring this technology to an industry for some kind of climbing as well as inspection based robots. So the next module which I would like to discuss to you is something related to a soft robotic fish. So we have developed a small fish kind of underwater robotic fish for a soft robotic application. So as far as fish is concerned, three major things which we need to consider. One is obviously the actuator. Second thing is the buoyancy. So because the buoyancy is going to play a major role, which is being well taken care by the body as well as the fin. So as far as any fish is concerned, so you will be having a head, we have a rib, and we have a cloudless fin, which takes care of the swimming action of it. So what we made is, we took a complete skeletal structure of a fish, and we just discretized into different levels. And what we took is, we took the bone arrangement and the nerve arrangement, and those bones and nerves are being replaced with shape memorialized spring. So in fact, this is a kind of theoretical investigation which we did. So basically, whenever before directly working on the field, so we used to do a theoretical simulation on our design to see how well these systems are working. So here also, we could see we have a middle portion. So we have just discretized our system into the cloudla filled region, the main body region, and the head region. So in the head region, basically all our power supplies, etc., we are planning to keep it. And from this, then a relay kind of circuit arrangement will be made, and this relay kind of circuit arrangement will be highly helpful for me to actuate my spring for moving it in a stroke. So basically, we could understand that with the availability of the shape memorialized spring, so we could go for a frequency of 0.1 hertz and 0.5 hertz, which will give me a stability in my buoyancy. So for that, we went for a complete theoretical analysis with respect to time and with respect to displacement, and we were trying to look into the overall behavior of it. In fact, since we were more interested into the kinematic analysis of it, so we took a fish head. So with along the fish head, we did a kinematic analysis. So in fact, we identified our key locus point, and from these key locus point we were trying to study the overall behavior, and then with respect to that we could able to fix up our fin position, and in fact we created a transformation matrix, and this transformation matrix helped us to understand to design our overall kinematics of the system as well as the buoyancy involved in it. Okay, in fact, this is the cloud law fin simulation. So, in which we, as I have discussed earlier, so we discussed our section into head, a body link, and a cloud law fin. So, our since we had a 3D printer in our laboratory, so we printed our head, we printed our body link, and inside this body link we had a SMA spring which is being well connected, and then we had a cloud law fin. So this cloud fin was developed using a polymer kind of structure, so that this polymer structure will flap. Okay, so this is a fabrication of the overall fabrication of the fish, where, as I have mentioned, so this is the SMA spring, and this is the 3D printed structure, and this is the cloud fin which is being placed over here. This is our control circuit what we have employed. So the interesting part of this control circuit is we made an Arduino board with an individual relay, and these individual relays were connecting our SMAs in a sequential manner. Like if you see, these two are connected, these two are connected, these two are connected, so that the forward stroke will be balanced by these relays, so that you can have control over the locomotion. So this was an arrangement what we made. So in fact, we did some kind of performance evaluation analysis. We made a small tank. So in this tank, we filled with a liquid, and we just integrated our fish into it. And there was an LDS sensor which was placed. So using an LDS sensor, we could able to see how it is moving up, and we were trying to study the displacement and the time. Okay, so in fact, we did a complete performance analysis where we have integrated with SMA, and then we were trying to study the bend angle. So how much is the maximum bend angle you could achieve, and how your response time is acting on the system to take care of the bend angle movement. So in fact, so it is something like this. So your response time will have its own effect towards maintaining the buoyancy as well as for the movement of the system. Okay, so this was a kind of performance evaluation we did with respect to an undulation along the right, along the left, and along the movement. And we almost monitored the amount of force which is exerted by these kind of SMA based robotic systems and its overall behavior. Okay, so this will give you a better clarity. This is with an onboard controller. So for initial level, we were taking care of the buoyancy by putting up our onboard controller over here. And this is our robotic fish, where you could see this is a training which we have performed on an underwater condition. And this is a complete locomotive movement which was coming up. In fact, currently we are working on a system where we are trying to integrate our onboard controllers inside the head. And the most important thing is like the power consumption is a major key. So what we are trying to do is, so we are trying to integrate some kind of piezoelectric structures on these materials, so that when you go it on an underwater condition, from an underwater condition, because of the load acting on it, it becomes self-energized and you can use it for your application. So these are some of the parameters we went for a performance evaluation. And these are some of the summary with respect to this, where we could see it has a velocity of around 25.5 mm per second. This was the velocity at which it was moving. And now we are in the mode of improving its behavior. Okay. So the next one which we are going to talk about, the next model which we are going to talk about is a kind of a soft robotic gripper. Like so we are I understand that we are happy with our fingers, so because these fingers has a very good capability with respect to your degrees of freedom, as well as it has its own sensing capability. So we had an idea in mind, why can't we develop a system which almost has a capability similar to the spring, so that whenever we are trying to hold any kind of delicate object, it should not exert pressure into it. So for that, we what we made is we made a kind of a composite structure. So we integrated our shape memory alloy wire inside this composite structure, so that these composite structures are being well actuated with these shape memory alloy wires. And whenever you are trying to apply a pulse to it, it can actuate in such a way that it can hold it. So in fact, this is a theoretical simulation we did along with a thermographic image. So this is how your structure looks like. So where you have your composite and you have your SMA wire is being integrated into it. So when you try to actuate it, there will be a deflection in this direction. And where we are trying to study your surface temperature as well as your wire temperature. So this is a mechanism which we have performed in our lab. So what normally we do is we take an application, we select our material. In some cases, we fabricate our material, or in some cases, we buy the material and we make our system. So this is one methodology what we have employed to make our system. So basically, we made a CAD model, we print a 3D printed mold, and this is an SMA fixed mode where we are trying to apply a strain to it. And this is a kind of arrangement what we made, and we use some kind of composite structure which is being embedded into it. So the first one which we need to look into it is basically we were more interested about its functional characteristics. So what we did is, so we had a SMA embedded soft actuator over here, and this is a laser displacement sensor. So we were trying to apply an electrical biasing to it to see how it moves and how the signals are being tapped and how its performance are being evaluated. Okay, so this is how the performance evaluations were made. So what we did is we went to a maximum displacement, even though our displacement is very limited. So we would like to see when we go for a maximum displacement, how does it behave, and when it goes for a minimum displacement, how the displacements are controlled with respect to time. So what we did is we fixed our displacement as 7 mm, and we were trying to switch within this and to see its performance behavior. And this is the displacement with respect to current, how we have applied over the behavior of it. And we are also more concerned about the overall reliability of these systems. So what we did is, so we went for a performance evaluation, basically the pre-straining effect and the displacement. And with respect to the pre-straining effect and the displacement, so we were trying to see the mapping behavior of it. So this is the soft gripper kind of arrangement, and this is an SMA integrated PDMS soft actuator, and this is an SMA wire which is integrated. So when you try to actuate it, you get a displacement coming out of it, and then you are trying to hold the system. So this is a video where you could see some kind of training we have applied to see how much it can hold. So this is at 2.5G, 3.5G, and this is a kind of arrangement what we made to see how it is to check its gripping capability. And we also checked it. So you can see a kind of stiffness which is happening. This is because of the actuation behavior of it. And we could see how long it is holding it and how much it is trying to apply a pressure on this. So you won't find any kind of deformation over here. So that is an interesting part with this. And this is a overall behavior of these PDMS structure where we could run it at different cycles and we could see its performance. The fourth important module which I would like to see is, so this is one of the projects which we were working with DRDO to develop some kind of jellyfish kind of arrangement. Like the motivation behind this system is basically like in the case of Bombay attack. So Mumbai attack, we all know. So the terrorist was diving in a lake. So the idea of this system is, so we have a jellyfish kind of structure. So this jellyfish will be on a floating state. Whenever there is a disturbance in the water layer, so it will have an onboard camera. It captures it and it sends immediately the signal to the concerned control room, so that they can map it and see whether the concerned person is. So that is one. So that where you have a very less lake kind of arrangement, and we want to make it swim. Second interesting aspect in using such kind of soft robotics smart actuator is, like this doesn't give any noise. Like if you want to escape from an enemy radar, or sometime you have a submarine and where you want to go for a surveillance, normally the pickup comes from the motor. The noise pickup comes from the motor. Whereas in this case, you don't have any pickup. So basically the noise, it's a noiseless actuator where you are integrating a shape memory alloy and you are trying to pick up the signal. Okay. So And this is how we have fabricated our structure. So this is a polyamide where we have a through holes, and we are trying to integrate some kind of SMA wire in it, and we are trying to actuate it. So in this actuation, what we are doing is, so this is a kind of prototype what we made. We made a small kind of rubber string, so that one-way actuation is taken care by a shape memory alloy, and the return actuation is taken care by the rubber string for a movable flap. Okay, so this is the kinematic model of the spin what we made. So that one thing is, it is highly flexible. So that is one interesting challenge what we were facing into it. So in this flexibility, what we made is, we were trying to actuate it and see its overall performance of it. So we went for a complete kinematic analysis, and in fact, we went for a complete dynamic modeling to see how the links were behaving. In fact, this is a kind of simulation results where we could see that we discretize our link into link 1, link 2, and link 3, and then we could able to see how these links we are generating their trajectories, and how these trajectories are picked up. In fact, here you could see how the trajectories are picked up and how the fin modeling will work upon. So this is the overall modeling of SMA polyamide, where we have a rubber string and we have a structure over here. And this is the concerned equations we have derived for studying the overall behavior of it. And we have done a complete theoretical modeling to see the overall actuation analysis with respect to different loading conditions, as well as we did some hydrodynamic analysis also. As far as in this hydrodynamic analysis is concerned, so what we are doing is, so we have a complete a hydrodynamic behavior. So in this hydrodynamic behavior, we were trying to, so we were applying a load, a hydrodynamic load towards the surface, and we were trying to study how these hydrodynamic loads have its own impact towards the actuation characteristics. So in fact, this was a complete jellyfish flapping motion which we have employed to study the overall hydrodynamic behavior. And this is a complete static analysis which we have employed, static and a dynamic analysis which we have performed to study the overall vector behavior in detail into it. So this is a kind of, so we almost oriented our robot at different levels. One is along the vertical direction, as well as one is along the horizontal direction, and how our system is behaving throughout. Okay, so this is a kind of a vortex motion, so which we have taken from a original jellyfish, and the same things are being incorporated well with respect to an expansion and a contraction of the system, which we have done as we have simulation results. And then we were also able to capture the force which is being exerted to it. In order to monitor the force, in fact, we made a small setup which with a force sensor, basically an with a small load cell, and over this load cell we have kept our system, and we were trying to study the overall characteristics of the loads. Most important thing, you might ask me a question. So since it is with heat base, when we try to immerse in a water condition, how does the heat transformation occurs? So even though we have a thin layer of polyamide over here, so this heat transformation is well studied. So that is, when you try to immerse it in a water, so you have a laminated layer over here, and from that we were trying to study the overall heat transformation characteristics. In fact, this is at rest condition and this is at actuation condition, where we could see the overall actuation were well taken it up, and we considered each and every individual tentacle, and the actuation behavior of this individual tentacle were investigated with respect to the different frequency analysis. So for investigating the performance analysis, what we made is, we just integrated our flux sensor, and this was a kind of an arrangement where it is completely transparent, and you have a camera which is being integrated into it. Your tentacle were made to move back and forth, and from this flux sensor you are trying to tap the signal, and we were trying to collect the buoyancy. In fact, this is a kind of experimental setup which we made in our lab, where we had a load cell and a tie rod kind of arrangement and a soft robotic jellyfish, and this is a water channel. Through this water channel, we were trying to give different signal, and we were trying to pick up the system. Okay, so this is an actual jellyfish, in fact, an image of an actual jellyfish, and this is how our jellyfish structure was moving. So we could able to tap the movement, and we could able to see how these movements are working upon. In fact, this is one kind of jellyfish where it has a kind of a vertical movement moving along the water. We were trying to biomimic this vertical movement towards our jellyfish for the onward stroke. So basically, when we are designing the system, two things which we were considering. One is it should float under the, it should have a capability to float in a particular bed layer. Another one is it should have a capability to reach the depth and pick up the signal. Okay. So if for all these cases, the jellyfish should have a capability to work upon. Okay. So we did some complete analysis. In fact, one major issue is basically the power consumption, because on a lab scale you can supply a power, but when we try to put it in an underwater condition, really we need to work upon. So what we did is we just integrated some kind of insulated batteries, and through these batteries we were trying to transmit the power and see what is happening. In fact, this is the final setup what we have transferred to our requester. Basically, so we made a complete polyamide integrated flex sensor, and this is a kind of PDMS structure kind of arrangement, and this is the sonar sensor. So in this sonar sensor, you have a layer where you have a sonar as well as a camera over here. So when it goes to a deep, it can pick up the signal, and it can be easily seen to it. So it has. So we have integrated a complete onboard electronics and a camera module in the system, and we were trying to look into the overall capability of it. Okay. Next important system which I would like to say is, in fact, this is a quite interesting system. Like you might have seen a petal of a lotus leaf, okay, or any kind of flower. It will be too delicate. So we want to mimic such kind of arrangement for some kind of micro mirror application, because the interesting part of this material is these materials are metallic based. So and one more thing, it can actuate. So these kind of metallic materials, when you try to actuate it, it can flap, and then in the meantime it can be used for diverting the beam also. So one more thing is, so we want to make some kind of dragonfly kind of arrangement. That was our main motto. So we developed a small actuator. So for such kind of dragonfly arrangement, commercially in the market you cannot find any kind of actuator. So we designed our own actuator. So it is called as Bimorph. So the interesting part of this Bimorph is you have a SMA thin film and you have a polyamide structure. So we have seen when we try to apply a heat to this SMA, basically it is going to bend, it is going to actuate, or it is going to bend. The return stroke, you require some effort to do it. But what we have done is, since we have integrated with polyamide, so the return stroke automatically comes from the polyamide. So that is an interesting aspect we have done over here. So this is the Bimorph, which is kept in on a heating plate. When we try to heat it, it unfolds, and when we try to cut off the heat, it comes back. Okay. So this is the modeling of the shape memory alloy Bimorph, where what we have done is, so we have just kept a point contact, and we are trying to study the overall behavior of it. So we did a theoretical simulation to study its performance, and this is how we have fabricated our actuator. So we took a polyamide with different thickness. So we integrated that polyamide along with a heater, and we were trying to evaporate the material so that when it is heating, so we have applied a strain to it. So there was a strain which was applied, and when we try to apply heat to it, it gets heated up, and finally you can see the actuation. So this was an experimental setup which we did in our laboratory for performance evaluation, because the handling a thin film is something different, because if you have a bulk structure like a spring or sheet, the ball game is different, whereas with a thin film you need to take up different characteristics, which is being well taken over here. What we did is we made a sample holder where we had a point contact into it, and then it was connected to a program power supply, and using a lab view we were trying to look into the overall behavior. So this was a performance evaluation characteristics which we did for it. So in this performance evaluation characteristics, we varied our thickness, and we were trying to look into the overall behavior in detail. And this is the control strategy which has been employed for it. So we kept our set point, and we went for a complete controller tuning to study the overall control characteristics in detail. So this is the SMA Bimorph with set point, so that you can see its actuation, and by restricting its actuation, you can control the set point. In fact, I can come directly to the application where we have made. So this is the SMA Bimorph based prototype, and this is a mirror kind of arrangement. So we made a 3 link out of it. So when you try to actuate it, you get a kind of movement over here, and this movement is being well taken care. Okay, so you have a programmable power supply, and you have a kind of steward platform kind of arrangement, and this steward platform is being taken care of. So this is the work volume of a SMA biomap. This is with actuation, after actuation, and this is an one leg actuation with a vertical movement where we could see the movement coming out of it. So you could directly see the structure working upon. Okay, so with this, I would like to conclude my presentation. So before concluding it, I would like to show a small video about our laboratory and the other laboratory work what we are doing. So basically, this is about our lab. So these are some of the facilities which are there with us. So you are free to use it anytime. So you can just write to me. I can help you. So we have a strong thin film fabrication, lasers, material characterization, including a temperature controlled UTM. So we have a strong control system as well as pneumatic based systems which are available. So this is a metallic 3D printer which we have demonstrated in our lab. Basically, this is completely developed in-house. So the main objective of this 3D printer is to print shape memory alloy structures based on your requirement. In fact, we were trying to fabricate a shape memory alloy based gripper, a bulk gripper for some kind of nuclear reactors, which we have fabricated using this. Commercially, so if you try to get such kind of wire arc based additive manufacturing, you may need to go up to something around few crores. Whereas this we have developed in our lab, including the software, at a cost of something around 4-5 lakhs, and now we are in the process of selling these such kind of additive manufacturing unit to different colleges. So if required, you can contact me. So it has a capability to control the crystal size, and even you can build a sphere of around 30 centimeter using this. And only thing is you need to have a wire spool. Okay, so the next one is, this is a kind of shape memory alloy welding, because welding of shape memory alloy is a challenging task, but weldability of the shape memory alloy has its own application towards aerodynamic structures. So we have opted for this friction stir based welding, where using friction stir based welding, we could get a better actuation. So this is one study where we were trying to look into the actuation behavior as well as life cycle behavior of these friction stir welded samples. So there was an LDS sensor, and this is a board which we have 3D printed in our lab. So this is a kind of a life cycle setup which we did for actuating our shape memory alloy with a laser. So it's a non-contact based system. Here there is a load is there available. Sorry. So here there was a load which was there available, and this load was something kind of actuation we were trying to study. So we are also involved in some kind of consultancies related to die-less manufacturing, which we call it as laser forming. So this is a laser forming which we are doing it on a sheet without using any die, because die cost is quite heavy. So here we don't use a die. It's a kind of a die-less manufacturing. We are trying to bend the structures. In fact, we have demonstrated, some of our technology is demonstrated to some companies like John Deere, etc., for making engine cabinets, prototype engine cabinets, and we have also demonstrated with Wapco for making some kind of brake pedals, etc. This process is called as laser shock peening process. So the interesting part of this process is like you are improving the residual stress. This is an SMA integrated flapper, which was developed in collaboration with DRDO. So the main objective of it is you can just actuate this flapper. Okay, so it is mainly meant for maneuvering of missile. This is a kind of SMA integrated heat engine. So you have a hot water. Based on the hot water, it is rotating. So this is a demonstration of a bimorph. So you have a hot plate. Over the hot plate, we are trying to put it, and we are trying to see its actuation behavior. In fact, bimorph on an Indian context, we are the first to demonstrate it, a bimorph over here, and we are trying to realize its applications. So this is some kind of laser-based actuation of bimorph. This is an SMA-powered jellyfish for which we have discussed in detail. This is an SMA actuated robotic fish with onboard controller. So we also develop some kind of lead-free piezoelectric actuators. Basically, piezoelectric actuators which we get it in the market are has a lead. So in fact, there is a ban from the government to not to use lead-based actuators. And so we have developed our own zinc oxide-based lead-free actuators. In fact, here one student he has made a mat out of piezoelectric. So when you try to stamp it, there is a kind of EMF which is generated, which is scattering his chemical reaction. So he's Dr. Rajagopalan, so completed his PhD from our lab, and he has developed a piezoelectric structure. In fact, we have also demonstrated some kind of burglar alarm. So this is a kind of device what we have made it in a mat, so that if some burglar try to stamp on it, immediately it will give an alarm. Second thing which currently we are focusing upon is like harvesting energy from the fluttering flag. So what we made is we made a thin piezoelectric structure. So this is a wind tunnel test where our flag is made, and when we try to flap it, because from the fluttering you are trying to harvest the energy. In fact, it is on the order of few milliwatts order, which is quite sufficient enough to charge your mobile phone, etc. So currently we are working on with DRDO to develop some kind of flexible shoe soles, so that when the soldier walks, and there will be a cap over here where he can keep the cell phone in it, and how much ever he walks, based on that his cell phone gets charged. So this is one system what we have developed for harvesting energy from the machine tool. So in fact, here there is a compressor is there where we have kept a piezoelectric, and we are trying to harvest the energy from it. So in fact, it has a dual application where you can employ for both monitoring of the system, which is which can cater the industry 4.0. Another one is you can harvest the energy. Okay. So with this, I would like to close my lecture. So I would be happy to address any kind of questions or queries raised by the.
Yeah, thank you, sir. It's really a warm lecture with us. And right now, sir, we have the few faculty member with us. We have Dr. Pradeep Kumar Kar, sir.
Nice.
Dr. Pradeep.
Yes, good afternoon, sir. It was very nice presentation, sir.
Thank you.
Thank you. I have one doubt.
Yes.
When we use the SMA-based fish robot, and it could be applied in real life, it means underwater condition.
So, sir, I couldn't hear your voice. When you use a SMA fish robot,
yes, in the underwater condition, then how we can control the thermal loading? How we can apply the load?
How we can apply the thermal loading?
Yes, sir.
Okay. See, as far as in this underwater condition is concerned, so wherever we are using the spring, so we are encapsulating with the polyamide. Okay. So what happens is this when your actuation happens in it, so you are somehow restricting your heat transfer. So on the other end, this encapsulation will also helpful for me to exert certain amount of load rate. So that's how we are trying to avoid the thermal loading in the system. Okay. So most important thing is currently it is moving up to a depth of around 6 to 8 meters. Okay. But most of the thermal loading will be highly will be heavy when it goes beyond 20 meters. Okay. So that what we do is we try to encapsulate a kind of silicon rubber kind of arrangement, so that this is completely insulated from the underwater condition.
Okay, sir. Thank you.
Thank you, Dr. Pradeep. We have Professor Mayank Dwivedi with us. Professor Mayank.
Good afternoon, respected sir.
Yeah, good afternoon.
Sir, actually, I have a query. Sir, is it possible to use shape metal alloy in space?
Yes. See, recently, two important applications I will tell you. This shape memory alloy also has a capability of pseudoelastic. That means it can absorb the vibration. So recently, from NASA, there was a video which was released where they have made a tire completely made out of shape memory alloy. So this tire can move along it, and then it can absorb the vibration. That is one. Second thing, this shape memory application was first started with space applications. Like Russian Sputnik had a deployable antennas made out of shape memory alloys. Okay. In fact, they had a small shape memory alloy based collet arrangement also for detachable collet arrangement for detaching a kind of satellite or something like that with shape memory alloys. So currently, we are working with ISRO in developing some kind of cryogenic based sensors using these shape memory alloys, which currently we are on talking terms, and soon we will be working with them.
Thank you very much, sir.
Thank you, Professor Mank. Sir, I would like to say once again, thank you for this special session. And in future, again, we are going to be connect in any sort, either the laboratory portion, either the lecture and session portion. I also want to say thanks to our panelists, Dr. Pradeep and Professor Mang, to be with us. Thank you, sir, on the behalf of Technical Events at Pali University. Thank you very much for your cooperation.
Thank you.
Thank you, Prakash, sir. Thank you.
Thank you, okay, sir.